Okay, colligative properties. We have to talk about this today because this is the lab we're doing. Why do you add salt to an ice cream maker?
Lower the freezing temperature.
Lower the temperature of the ice. If you try to make ice cream in an old-fashioned ice cream maker where you got, ice around the canister, if you don't put salt on it, the ice cream will not freeze no matter how much ice you put in there. Adding the salt lowers the freezing point of the ice and makes the ice colder. Yes?
Can you do that with alcohol? Make like alcohol cubes? Nice.
You can freeze alcohol, and you can freeze mixtures of alcohol and water, but you're going to have to get them colder than 0 to freeze. So we're going to observe this in lab today when we make ice cream. The temperature of your ice and salt mixture is going to get down to about minus 10 degrees Celsius. It's really cold. So freezing point depression is called a colligative property. There are several of them. Colligative properties are properties that depend on the number of particles in the solution, not on what those particles are. So if you add sodium chloride to the salt, or if you add potassium iodide to the salt, if you have the same number of particles, the freezing point will change by the same amount. It doesn't matter what those particles are. We do see, though, that colligative properties of electrolytes are a little bit different than non-electrolytes. Because if you have 1 mole of an electrolyte, like sodium chloride, when it dissolves, it forms more than 1 mole of particles, right? In theory, it forms 2 moles of particles. Whereas if you have a non-electrolyte like sugar, it dissolves in the water just fine, but if you put 1 mole in, you have 1 mole of particles. So it would take twice as much sugar to lower the temperature, the same as the sodium chloride. We see that vapor pressure is also affected. Vapor pressure lowering is a colligative property. So if we look at this beaker of water covered with a watch glass, evaporation, we've got evaporation and condensation, and it's in equilibrium. When you put salt in there, the salt essentially gets in the way of the water evaporating. It slows down the evaporation, doesn't affect the rate of condensation initially. And so more will condense until you reach a new equilibrium. The new equilibrium is going to have fewer gas particles. The amount of gas particles here is the partial pressure, or the vapor pressure, of the solvent. So when you put a solute into your solvent, the vapor pressure of the solvent becomes less. This is cool. And you could try this at home. I want to, but I don't have a cake plate, and it's just not enough motivation to go out and buy one. You put a glass with pure water and a glass with salt water and cover them. They're not touching each other. Cover them, give them a couple of days. Come back later, and the level of liquid in the salty glass is going to be higher than in the pure water glass. Does that seem impossible? I mean, that's just not something that people would say, oh yeah, that makes sense.
Is the water that vaporizes going into the other one? Or is it just
The water from this one, the water that was here, left and went into this one.
Okay. I wasn't sure if it was just not evaporating, that's why it was high.
No. It actually has gone up. It's not that it's just not gone down as much. The important thing is that you have this cake topper over it so that it can't escape. Otherwise, this would be lower, but this would also be lower. Not as much, but it would just be evaporating into the air. But what happens here is that the rate of evaporation of this one is higher than that one. And the rate of condensation for both is the same. And so you end up with a transfer of water molecules from one beaker to the other. And this is similar to the idea of osmosis. And so we can explain it in terms of entropy and the spread of energy. Of course, we can quantify this with an equation. Raoult's law quantifies vapor pressure. So the vapor pressure of the solution equals the mole fraction of the solvent times the partial pressure, the vapor pressure of the pure solvent. So if the mole fraction of solvent is 100%, that means it's pure solvent. 100% would be 1, no, I'm sorry, it would be 1, would be a mole fraction of 1 times the pressure of the pure solvent. And so the solution would be the same. If the mole fraction is half, if half of it's solvent and half of it's solute, then the vapor pressure of the solution will be half of this. So we see that vapor pressure is directly proportional to the amount of solvent. You can measure vapor pressure lowering. Stupid train. The change in vapor pressure, there's some math where you get from this one to this one, but I'm thinking nobody really cares, so I left it out. Mole fraction of solute times the vapor pressure of the pure solvent would give you the change. So we can do problems like this. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. Vapor pressure of pure water is 23.8 torr. So we need Rolle's law for this. So the vapor pressure of the solution equals the mole fraction of the solvent, which is water here, times the vapor pressure of pure water. Well, this right here is the vapor pressure of pure water. This is what we're trying to find. What's the mole fraction of water? Dang, we have to calculate that. Mole fraction of water is going to equal the moles of water divided by the moles of water plus the moles of the ethylene glycol. I'm going to call him EG. So how do we figure these out? We got to get grams to moles, right? So for the water, we've got 285.2 grams of H2O. Saying the G does not make it magically appear. And we've got the molar mass of water, so 285.2 divided by 18.02. So 15.827 moles. So that's one of them, 15.827 moles plus, and then 15.827 on the top. Moles of ethylene glycol. Well, we've got 55.3 grams. And so we need the molar mass, right? We've got 3 carbons, 3 times 12.01, and 2 oxygens, and 2, 4, 6, 8 hydrogens. I'm getting 76.09.
All that, and it's 76.
Yeah. So 55.3 divided by 76.09. And that should have 3 sig figs, 7268 moles. So we'll put that in there, 0.7268 moles. Fifteen point eight two seven divided by the quantity 15.827 plus 0.7268, 0.9560. No units on that, it's a mole fraction. So the mole fraction is 0.9560, and the pressure of the pure solvent, the vapor pressure, is 23.8 torr. So we get 0.956 times 23.8. 22.8 torr. So putting the ethylene glycol into the water lowers the vapor pressure of the water. Yes?
Why don't we convert that to ATM?
Well, we could convert it to ATMs, but we don't have to. I like unit conversions, but I think I've done enough math. So because the mole fraction has no unit, unless it specifically says, you know, what's the vapor pressure in atmospheres or pascals or something, you can do it anything you want. And so since this was given in torr, it's easiest to give that in torr. Any questions? Oh, I forgot about all this stuff. We've got to get to the freezing point depression. No, we don't want to skip this. When the solute is volatile, when it vaporizes easily, it actually adds to the vapor pressure of the solution. And when we talk about an ideal solution, it's going to follow Raoult's law at all concentrations. So the total vapor pressure is the partial pressure, the vapor pressure from the solute plus the vapor pressure from the solvent. But sometimes the interactions between the solute and the solvent are really, really strong. So the solute and the solvent are just like really liking each other, and so then neither of them evaporates as easily as it did alone. And so that makes the overall pressure lower. Sometimes they're in a solution, but they really do not like each other, and so they actually vaporize more quickly than if they were alone, and that raises the vapor pressure. And so here are graphs showing deviations from Raoult's law. So this is an ideal solution. So here we have mole fraction of component A going from 0 to 1. This is the vapor pressure of pure A. And here we have the mole fraction of component B going from 0 to 1. And here is the vapor pressure of pure B. I'm sorry, this isn't the mole fraction. This is the vapor pressure. We're looking at the mole fraction of A. So over here, we have no A, we have all B. And so the vapor pressure will equal the pressure of pure B. And this purple line is just the sum of the red line and the blue line. Isn't that nice how they used purple, because purple is red and blue combined together. If there's strong solute-solvent interactions, then these lines deviate from what we expect from Raoult's law. And so the vapor pressure of each component is lower, and so then the overall vapor pressure is lower. And this is the opposite, where they don't like each other, and they'll evaporate more quickly. Thankfully, we don't have to do anything about that. I didn't do this problem yesterday because I didn't feel like it, and I'm not going to do it today either. I will try to find it in a previous lecture and stick it up for you, but it's just, this is so tedious, I can't stand it today. I just can't. Somebody needs some ice cream. We're each making our own ice cream. It's going to be awesome. Anyway, so here, phase diagram. We're getting there. As soon as we get to the equation, we'll stop. So here's our phase diagram. What happens when you add a solute is that these curves become lower. So this evaporation curve becomes lower. What that does, here's the boiling point where the atmospheric pressure is equal to the vapor pressure. And so it moves it out. It causes the boiling point to go up. It causes the freezing point to go down. I used to have trouble remembering which way did they move. I knew they moved, but I couldn't remember which way. They move away from each other. So it expands the temperature range over which it will remain a liquid. It lowers the freezing point, raises the boiling point. Here we go. Freezing point depression. It's really the vapor pressure lowering that causes this to happen. Here's our equation for freezing point depression. Delta TF, the change in the freezing temperature, equals the molality, that's stupid unit again, times a constant. And that constant is going to depend on the solvent. And I hate it when they make exceptions like this, but a freezing point depression really should be a negative number. You should take the final minus the initial. But for whatever reason, they don't do that. They always express it as a positive number. So we're just going to have to deal with it. Delta TF is the change in freezing point. We've got molality of the solution and the freezing point depression constant. So here's some constants. And the normal freezing points, and here are the freezing point depression constants. So the unit is usually degrees C per molal. Yes?
So what are we going to use as the constant for this?
Well, since we're using water, we're going to use the constant for water, which is 1.86. So we'll do this one example, and then we'll make ice cream. Calculate the freezing point of a 2.6 molal aqueous sucrose solution. Well, delta TF equals the molality times KF. Go back to the table, KF, that wasn't a very nice F. KF equals 1.86 degrees Celsius per molal for water. This is a nice problem. They just gave us the molality instead of making us do all those stupid calculations. So 2.6 molal times the constant. This is 4 something. 4.8. And the unit is degrees Celsius because the molalities cancel out.
So molality is not something we can just calculate. We have to do all the first step.
Well, molality can be calculated, but you need the moles of solute and kilograms of solution. 4.8 degrees. Is that the freezing point?
That's the change.
It's the change in the freezing point. What is the normal freezing point of water?
0.
0. So what do I do to find the new freezing point? I subtract this. So the freezing point was 0, and this means it's going to be this much less. So the freezing point is negative 4.8 degrees Celsius. We're going to stop.